Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to discuss. First, I refer to the last topic. Last time, that is in last lecture, lecture 5, we were discussing the properties of electric charge. So it is continued. Properties of electric charge. Actually, these things you know from your previous study. You have done it in your class 12th. I'm just revising these ideas. So in last lecture, we talked about additivity property of electric charge. Second thing, we talked about conservation. Said electric charge is conserved. All reactions conserve electric charge. There is no exception to this law. And we explained additivity. Now today, we are going to discuss the third property, which is quantization. Quantization. Electric charge is quantized. Electric charge is quantized. Conservation means electric charge is conserved. Quantization means electric charge is quantized. What is the meaning of that? If Q is the electric charge of any body, which we measure directly, then it has the property that it always obeys this equation. Q is equal to plus minus NE. Its meaning is, first, what's N? And it can be 0, 1, 2, 3, and so on. And E is the amount of charge on the electron. That is, E is 1.602 into 10 raised to the power minus 19 coulomb. Quantization means the charge we measure Q of any body always obeys this relation. That means either the body is neutral, that has no charge, then N is 0. Or if it is positively charged, it can have plus 1 E, N is 1, plus 2 E, N is 2, plus 3 E, plus 4 E, and so on. Or if its charge is negative, it can be minus 1 E, N is 1, minus 2 E, N is 2, minus 3 E, and so on. It cannot have a charge in between. That means it cannot have a charge 1.2 E, minus 1.3 E, 6.2 E, minus 6.2 E, minus 5.1 E. These things are not possible. That means when it has charge, this is not possible. Not possible. Not possible. That means when it has charge, the minimum possible value of charge is E. then all higher charges are integral multiple of this particular unit. This is the meaning of quantization. And the smallest value of charge, all higher values are integral multiple of E. The smallest unit of charge which a body can have is called quantum of charge. So E is quantum of charge, quantum of electric charge. So our electric charge is conserved. There are other physical quantities which are conserved, but there is conserved, and there are other physical quantities which are quantized. But you have to remember, whenever we say something is quantized in physics, that means the quantity has certain minimum value possible, and all higher values are integral multiple of that, and the smallest possible value which it can have, that's called quantum of that particular physical quantity. Here E is the quantum of electric charge, right? The next thing is Coulomb's law. Coulomb's law. Coulomb's law is actually force law in electrostatics. It states that if we have 2 point charges Q1, Q2 separated by distance r, now we know there will be electric force between them, which can be either negative or which can be either repulsive or attractive. And repulsive, it will be repulsive if both charges are like, both positive or both negative. It will be attractive if charges are unlike, that means Q1 positive, Q2 negative, or Q2 positive, Q1 negative. So electrostatic interaction is of two kinds, attractive or repulsive. Now Coulomb's law says if you have 2 point charges Q1, Q2 separated by distance r, then the magnitude of electric force F between them is proportional to the product of charges and inversely proportional to square of the separation distance between the charges. The constant of proportionality here is written as K Q1 Q2 by R square. This K is sometimes written as 1 by 4 pi epsilon naught. So we write F is equal to, instead of K I write 1 by 4 pi epsilon naught Q1 Q2 by R square. So this equation gives me the magnitude of electric force between 2 point charges separated by certain distance r. The nature of force, it can be repulsive or attractive depending on relative sign of the charges. Now this equation is valid when Q1 and Q2 are placed in vacuum. If they are placed in some medium, then we have to divide this force by the dielectric constant of that particular medium, right? So it is the magnitude of the force. What about the direction? Direction of this force is along the line joining the charges. This much you know. Direction of the force is along the line joining the charges. What about the value for constant of proportionality. So value of k is 9 into 10 raised by 9. What will be its unit? Newton meter square per coulomb square. Newton meter square per coulomb square is the unit. So here you have force, and you solve for k, it will be Newton on this side, and it's r square. When you go this side, meter square, this q1, q2 will be in terms of units coulomb square. That will go downstairs, so it will be Newton meter square per coulomb square, right? This epsilon naught sometimes is called permittivity, not sometimes, always. It's called permittivity of free space, right? So you can compare this with Newton's law of universal gravitation, this equation, then make the comparison. You know, Newton's law of universal gravitation gives us the gravitational force between two point masses. Let's say if you have 2 point masses m1, m2 separated by a distance r, and the gravitational force between them is proportional to product of the masses and inversely proportional to square of the separation distance. Here constant of proportionality is called universal not universal gas constant, universal gravitational constant. It is called universal gravitational constant. Its value is 6.67 into 10 raised by minus 11. Unit will be in SI system Newton meter square per kg square. Newton meter square per kg square. Direction of the force is along the line joining the masses. Now, what are the similarities between this and electrostatic force? One similarity is here electric force is directly proportional to the product of the charges. Here it is directly proportional to product of the masses. So role of mass here is in Coulomb's law replaced by charges. Distance dependence is same. It is inversely proportional to r square. Same is the case with Newton's law of universal gravitation. So sometimes we call these forces as inverse square laws, right? These are similarities. One difference is here forces of two kinds, because charges are of two kinds, positive and negative. Here force is only of one kind, that is attractive in nature. The difference you can see, you need to note this, the value of constant here is very small compared to the value of k. K is 9 into 10 raised by 9 Newton meter square per coulomb square. But this is 6.67 10 raised by minus 11. So you need to remember this. That indicates only this thing, that the gravitational interaction is very weak compared to electrostatic interaction, right? Another difference I want to mention here is that gravitational force is not screened. That means if there is some force between two masses at certain distance in vacuum, if you fill this vacuum with some material, force is not going to change. But in electrostatic force, there is shielding possible. That means in vacuum you have one force. If you fill the vacuum with oil or some other material, force will change, right? So it depends on in which medium charges are placed, right? But here that is immaterial. So this was Another thing we have to discuss next topic. When we talk of this electrostatic interaction, there are two possible descriptions for this force. Two descriptions, or I say there are two points of view. One point of view is called action at a distance. Action at a distance idea. Second idea is field idea. First, I discuss the meaning of action at a distance. When we say or when we describe electrostatic interaction using this action at a distance idea, in this action at a distance idea, we say, listen carefully, we say here the interaction between the charges, between the charges is direct and instantaneous. Direct and instantaneous. What is the meaning of that? Direct means there is no intervening agency or no third party. Meaning, if I have two charges, Q1 exerts directly force on Q2 and Q2 exerts directly force on Q1. There is no third party between Q1 and Q2 in this interaction. No third party, no intervening agency. That's the meaning of direct, right? Sometimes symbolically, this action at a distance idea is represented this way. We write charge, then we show a double arrow, and we write charge. By that we mean this charge directly exerts force on other charge, and this charge exerts directly force on this charge. What is the meaning of instantaneous? Another thing. Instantaneous. Meaning of instantaneous is if you move Q1 and keep Q2 fixed, what will happen? Q2 will sense Q1's movement. How? We said the force is K Q1 K Q1. Let me fix this. Let me fix this first. Okay. We said this force is K Q1 Q2 by R square. So if you increase the distance between the charges, force will. If you increase distance, force will decrease. If you decrease distance, force will increase. So if Q1 is moved relative to Q2, you can either bring it closer to Q2 or you can move it away from the Q2. If you bring Q1 closer to Q2, force on Q2 will increase. So in that sense, it will sense its movement because it the force on Q2 will change. If you move Q1 away from Q2, force on Q2 will decrease. So that way it will sense movement of Q1. Now the question is, when I move Q1, when will Q2 sense that? Instantaneous or action at a distance idea or description says that the moment you move Q1 is the same as the moment Q2 senses its movement. That means this effect is instantaneous, irrespective of the distance between the charges. I repeat, when I move Q1 at that particular moment, Q2 will sense its movement. Q2 will know at that particular moment that Q1 is moved, irrespective of the distance between Q1 and Q2, right? That means there is no time delay or time lag between the moment Q1 is moved at the and the moment Q2 senses its movement. That's the meaning of instantaneous, irrespective of the distance between Q1 and Q2. That, in other words, means that this effect, the interaction between Q1 and Q2, is transmitted at infinite speed. Because when we say effect is instantaneous, Q2 senses the moment of Q1 with no time delay, irrespective of the distance between Q1 and Q2, we are saying interaction is instantaneous. Instantaneous means this effect is moving from Q1 to Q2. Signal of this effect moves from Q1 to Q2 at infinite speed. Because if I say, for example, uh, speed is equal to distance by time. If I say something moves from point A to point B instantaneously, that means it moves this much distance in zero time. Denominator zero, speed will become infinite. Same is here. When I say the interaction is instantaneous, that means irrespective of the distance between Q1 and Q2, when I move Q1, Q2 senses its movement, and reverse is also true. If you keep Q1 fixed, move Q2, Q1 senses the movement of Q2 instantaneously, irrespective of the distance between them. That means this interaction is transmitted from Q1 to Q2 at infinite speed because it takes zero time for the signal to move from one charge to other charge. This is the problem with this idea. You know from your previous study that we have postulates of spatial theory of relativity, postulates of spatial theory of relativity. And one of the postulates of spatial theory of relativity is that speed of light in vacuum c, which is 3 into 10 raised to 8 meters per second approximately, is same for all inertial observers. Speed of light in vacuum c equal to 3 into 10 raised to 8 meter per second is same for all inertial observers. This c is the speed limit of this universe. speed limit of the universe. Speed limit of the universe. That means no particle or signal can move at a speed greater than c. Now this contradicts with action at a distance idea. When we say that the interaction between the charges is instantaneous, we contradict with this speed limit of the universe c. Is when we say it is instantaneous, speed is infinite, and then when we say it is infinite, it is greater than c. Therefore, this action at a distance idea has been discarded. So we have a new idea, that's field idea. And field idea, what we say? In field idea, we say that the interaction is neither direct nor instantaneous. Neither direct nor instantaneous. And symbolically, we represent this way. Charge, field, and charge. More specifically, we write here electric field. So idea is like this. We say if we have Q1 which is surrounding Q1 in this space, there is electric field. I think I should use another color for this electric field. Eraser. So if I have some charge Q1, surrounding this charge, there is electric field. That's my pen. There is electric field. There is electric field, right, of Q1. Likewise, Q2 will have its own field below. Q2 will have its own field surrounding it. We say if Q1 finds itself the field of Q2, that field will exert force on Q1. I repeat, Q2 has its own field, Q1 has its own field. If Q1 finds itself in the field of Q2, that field will exert force on Q1. Similarly, if Q2 finds itself in the field of Q1, that field will exert force on Q2. So field is the third party, right? Field is the third party. Q1 doesn't exert force directly on Q2. There is electric field in between them. Q1 has its own field surrounding it. Q2 has its own field surrounding it. So charge has field, charge creates field, that field exerts force, right? Now interaction is not instantaneous, means we say here if this is Q1, this is Q2, and there is some distance between them, If you move Q1 relative to Q2, Q1 or Q2 relative to Q1, this movement will not be sensed by other charge instantaneously. And what will happen? This interaction will move from Q1 to Q2 at the speed of light. That means if this R here is 3 into 10 raised by 8 meter, when you move Q1, the speed of light in vacuum is 3 into 10 raised by 8 meter per second. If there is 3 into 10 raised by 8 meter distance between Q1 and Q2, if I move Q1, Q2 will sense it after 1 second, because this interaction will take 1 second to reach Q2, right? Similarly, if there is, for example, this is my Q1, this is my Q2, and R is 1 light year distance unit, light year. The distance of the light in 1 year is light year. So if distance between Q1 and Q2 is 1 light year, if I move Q1, Q2 will sense this after 1 year, right? So interaction is not neither direct nor instantaneous. Now this field idea is in compliance with special theory of relativity. It doesn't contradict that. So this is the modern way of describing the interaction between the two charges, right? This is all for today. Thank you, and work hard, right? Don't waste your time. Be sincere to your studies, right? Assalamu alaikum.